conversation with the speaker. Okay, so welcome everyone. For those of you who are new to this seminar series, it is called Physics and Machine Learning Meets Engineering, and the seminar series has the goal to host talks at the intersection of these two fields. We are based at, the seminar series is virtually based at the Alan Turing Institute, which is the National Institute of Data Science and Artificial Intelligence of the UK. Today's speaker is Jordi Bolibar, who is currently a postdoctoral researcher at Delft and the Institute for Marine and Atmospheric Research at Utrecht University in the Netherlands. He obtained degrees in telecommunications, engineering, and worked as a software engineer before transitioning to geosciences and obtaining his PhD at the Institute of where he worked to model the evolution of alpine species and combining mechanistic models with machine learning to model, understand, and predict climate interactions at large geographical scales. So before leaving the floor to the speaker, I just want to remind the organizer of this seminar series. So my name is Andrea, and together with Davor, who is a PhD student at the Turing, and Zach Conti, who is the lead organizer of the seminar series, we host this type of event. Zach unfortunately cannot be here today, but usually this is the person who is organizing this event. So after I've introduced our speaker, Jordi, I'll leave the floor to you.
Thanks a lot. Okay. Can you see my screen?
Yes. Yes.
Okay. Let's see. Cool. So yeah, thanks a lot, Andrea. So yeah, first of all, thanks a lot for the invitation. Today I will be showing mostly the work I've been doing during my postdoc in the last couple of years, and it's a new project that I started together with mostly some people in the Department of Statistics at UC Berkeley. And I will be talking about Universal Differential Equations, which is something quite similar to neural differential equations, but applied to the modeling of glacier ice flow, and particularly using a new model that we're developing in the Julia programming language. So before diving in, let's see. Yeah, I will give some context a little bit on my research to show you a little bit like what led me down this path. So I don't know if you're or not familiar with glaciers, but basically glaciers, as you can see in this picture, they are, first of all, very beautiful, but also very complex. You can see there's a lot of stuff going on here. And it's precisely, at least from my point of view, this fascination about these magnificent natural systems and all the really complex physics involved that really led me to start wanting to study them. So okay, yeah. Before explaining a little bit like how we apply these methods into glacier modeling, it's interesting to understand a little bit like how glaciers work. So basically, a glacier is a perennial body of ice that forms in cold enough climates, and basically interacts with the climate via some family of processes that are called the mass balance, which is the consequence of the mass gained or introduced in the system via processes of accumulation that could be, for example, snowfall or avalanches, and the process of ablation that remove mass from the glacier, for example, the melting of ice or snow or fern, or when the glacier tongue comes into contact with a body of water, for example, a lake or the ocean. There's scalving, where basically there's detachments of blocks of ice that creates icebergs. But this is one of the two families of processes that dictate the glacier evolution. The second one is ice flow dynamics, that dictates the way ice flows downslope through the effects of gravity. And basically, it's the interaction or the interplay between these two processes that determines the evolution of glaciers. And this is exactly what we try to model with glacier evolution models. But of course, this is even more complex when we try to model all glaciers on Earth. Here in this plot, you can see in red, like all glaciers on Earth outside the Greenland and the Antarctic ice sheets. Basically, there's 200,000 of them. And you can see they're really situated in like everywhere in the world and with many different climatic regions. So basically, these models, when we try to upscale them or apply them at global scale, they have to be, first of all, like relatively computationally cheap. but also they have to be able to extrapolate a lot, so to be very generalizable, because they have to be applied in many different conditions. And also, it's very important to mention something that is driving our work right now, especially in the last decade. There's been a huge increase in the amount of satellite data, both like optical, radar, and also like gravimetry, in terms of observations of glaciers. Right now, all this wealth of data is precisely driving a little bit this data-driven modeling revolution that we're seeing in earth sciences, and in glaciology is like particularly true. So basically, it's thanks to these observations that now we're capable of calibrating or doing fancier stuff with models. As I said before, in terms of glacier modeling, we have the mass balance component related to the climate, and we have the ice flow dynamics component. So these are normally modeled separately in glacier models, and then we just like couple them. And of course, this can be approached in many different ways, like models range from empirical to more like process-based, and then some of them are statistical. And this is exactly what I did in my PhD. So what I signed up for my PhD, basically, like the original plan was to develop some statistical methods for glacier evolution modeling. But then when I started like dipping my toes a little bit, I realized that like, machine learning was actually super powerful and had not been applied yet to this field. So this was one of the first applications, and I developed like this model OGGM in Python that I applied during my PhD in the French Alps. I will briefly show you a little bit like what I did with this model, because it's a good example to show why I'm doing what I'm doing right now. And then this will be the main topic of this talk. It's ODINN. It's my current project and modeling framework. And basically the idea about ODINN is to mix machine learning approaches, so data-driven approaches, with more physics-based and process-based modeling, including differential equations into the mix. So yeah, during my PhD, basically what I did is I used purely data-driven machine learning, so deep learning, classic deep learning, quite simple, feed-forward neural networks, because we don't have a lot of data. So we need to use like some specific applications of machine learning that are not the ones that we see, for example, in the industry. And yeah, we basically showed that this work quite well in terms of methods. And then what we did, as I said, I in my PhD, I worked in the French Alps. And so we applied first to make reconstructions of like mass changes of glaciers in the region for the last half century. So basically it was kind of a fill the gaps. We had sparse observations, and then we trained deep learning method to kind of interpolate and reconstruct the full data set. And finally, what we did is we also applied this method to make future projections under different scenarios of climate change. So basically this allowed us to understand a little bit like the nonlinear sensitivity of glacier changes to different scenarios of warming. And it also helped us to account a little bit like of how much ice will be left in the Alps by the end of the 21st century. So yeah, this worked quite well. It was the first application of machine learning on this. And so we could learn quite a lot, but also there were some challenges and limitations. And the first one of them was that like we realized, like actually not something new, but like at least like from my experience, that inference is pretty complicated when we use a purely data-driven approach. Mainly because since we like our main choice, we also used other like machine learning methods, but our main choice was neural networks, and as you probably know, they're kind of like a black box model, so it's a little bit hard to understand what's going on inside. And also, this is important, especially in geophysics, because in this case, it's a bit hard to extrapolate beyond observations. Of course, we cross-validated the model thoroughly in order to make sure that it could make predictions beyond the observations, but still, it's always a little bit hard to make sure that it's actually learning the right thing. And then most importantly, because like at the end of the day, we are researchers, so we care about the physics, and it's hard to gain knowledge about the underlying physical processes that are like driving the nonlinear functions learned by the neural network. So overall, sometimes I like to show this cartoon because it shows a bit like the feeling that we can get with these sort of purely data-driven methods. Basically, it feels like we're pouring data into the system, then we're doing hyperparameter tuning, and we're doing like some little tricks in order to improve the performance, but it all feels very empirical. So in the end, it's just like, it's not very satisfying in terms of understanding of physics. So that's why by the end of my PhD, I kind of like decided like, well, maybe I would like to try new things to kind of overcome this these limitations, and it's when I started doing some literature research, and I saw that there were some new like research opportunities that they were trying precisely to tackle these problems. And this is where ODINN comes, my current project. And yeah, this is a little bit like what led me down this path. So ODINN is this current project I'm working on. And basically it is an open source modeling framework that we are developing. And it has two main research paths. The first one, what we're trying to study is applications of physics-informed for machine learning methods, precisely in the case of glaciers, but also a little bit more generally, like how we can apply it to differential equations linked, for example, to diffusivity, nonlinear diffusivity, and these sort of processes. And then there's another branch more dedicated to the applications, so global glacier modeling, so how we apply these methods in order to improve or create new glacier models that like work better. And then another important feature of this project is the fact that it's multi-language. So basically we're coding, the model is coded mostly in the Julia programming language, but we are also using Python because basically we need some tools that are only exist in Python. And basically this is another like strong point about like Julia, that they blend together really, really well. So we have this flexibility and we can have a little bit of best of both worlds of the two programming languages that I will show you in the next slides. So what is the idea of this project? What we try to do, like at the core, is try to discover new empirical laws governing large-scale glacier processes. So it's mostly an inference project, not so much a prediction project. And what we do is, like, as I said, we use the Open Global Glacier Model, which is a very well-known Python model, like a community model, and we use it purely to retrieve all the data and to preprocess it. So basically, in order to get our initial state for our simulations, we need, of course, climate data, we need ice thickness data, we need topographical data, and basically with this we can get our initial state. We don't have to recode what all glacier models use from scratch. We just reuse this, and for that we call it directly from Julia in Python. And then basically what we do is we feed this to our model in Julia, and then we do two things. The first one, which will be the main topic of this talk, is functional inverse modeling. This is what we'll mostly be talking about. And then, of course, we can do forward modeling, so predictions. And then we can, of course, like plot and do any analysis we want with all these outputs. And as I said, like this is in the title, of course. So this is really like the main methods or the main idea behind this project. It's called Universal Differential Equations. So Universal Differential Equations basically sit at the intersection of domain knowledge. So in this case, like the physics of glaciers, of numerical methods that allow us to solve the differential equations, and also data-driven models. In this case, we use machine learning or neural networks. And the idea is that, like, for example, this is the differential equation that describes the flow of ice. So basically, it's the mass balance part, the climatic component, and this dictates the flux of ice. So basically, the divergence of the flux. So this is the diffusivity, which is nonlinear, and it's driven by the surface gradient of the glacier. And if we model this purely in a data-driven way, this would be our model. Basically, we would model everything, all the dynamics directly from data. So it will be a purely data-driven model. But this approach, basically, what we try to do is a very targeted approach to machine learning. So we keep the structure of the differential equation. So we keep the mechanistic model, and we embed a neural network inside the differential equation, and we ask the neural network to just learn a subpart of it. So in this case, it could be, for example, the diffusivity. This is what we're working on right now. But in the end, it's flexible, so we can substitute the neural network with anything. It could be also this subpart of the mass balance, for example. And in the end, if you think about it in terms of philosophy, a little bit like in modeling philosophy, this basically has a little bit of a change, because basically it's sitting in these two steps. When we try to model a new physical process or a dynamical system, basically the first rule is make use of as much existing knowledge as possible. So if there is a differential equation or an equation that describes already quite well that process, let's use it. Let's use its structure that will better constrain our problem. And then let's only use regressors. So in this case, we use neural networks, but it could be anything. for the subparts that we don't know, or the subparts that we want to expand, that we want to parameterize, the ones that we have a lot of uncertainty and that we want to better constrain. So basically what we want to expand is this mix of like mechanistic models plus the flexibility of like statistical methods. And here, what I'm going to try to do is I'm going to show you an example with this equation that we're using, the Shallow Ice Approximation. And I'm going to first show the example of a classic single parameter inversion, the classic inversions that everyone knows. And then I'm going to scale them to functional inversions to show a little bit like the added value in terms of like modeling. So as I said, here we use the Shallow Ice Approximation, which is a very popular equation to describe the flow of ice in a simplified manner. And basically what it does is, it describes like the changes of the ice thickness with respect to time. And it has, of course, the climatic component, so like the mass balance. And here we have the flow of ice. And the diffusivity, as I said, is like highly nonlinear. It's pretty complex. And let's say that we want to calibrate the parameter of the diffusivity. In this case, what we are targeting, it's A, which is the ice viscosity. So depending on for example, on the temperature of the ice and other like physical properties of the ice, the glaciers will flow faster or slower. So will deform faster or slower. So like in very cold regions, the ice is very cold, so glaciers will flow slower, whereas like in more temperate regions or tropical regions, the ice is like more temperate or like warmer, and it will flow faster. So this is, for example, our parameter of choice in order to optimize. So what we would do in a classic inversion, basically we try. Of course, we have a cost function, a loss function that compares our observations with the solution of the solver with our initial state, a forward run between t0 and t1, and with a given a value. And basically, we're just like minimizing this loss function in order to find the best a value. Of course, this implies being able to compute the gradients of this. And if you think about what we obtain here, actually, it's the A value that we obtain here is stationary both in space and in time. So if we are inverting this for like a region, so multiple glaciers and for a period of different years, basically the best A value would be some sort of average value that fits best this region or this period. If we want to see the variability, we'd have to invert each instance, so each glacier or each year individually. And we could see some variability, but it's hard to understand what drives that variability. So basically this, in terms of like a comprehension or understanding of the physics, I mean, it serves to fit the data, but it's not super flexible and it doesn't give us a lot of clues. So this is where functional inversions come into play. So what we do here is like we stay exactly with the same equation, the same parameter, but we just do a tiny change here. So basically what we do is we substitute A in the differential equation by a very small neural network. It's called also A, and it has the theta, so its parameters, and we fit it an input feature that we determine as a proxy that could explain the variability of that parameter. So if you know, like in the physics, that this, for example, is driven by like the temperature of the ice or the local climate, the local topography, you feed those data into the neural network and you ask the neural network to parameterize that for you. So in this case, for example, in this toy example, we're using the local long-term temperature. So basically like a rolling mean of 30 years in the glacier. What happens here in terms of like optimization is that we are no longer optimizing like a single parameter. What we're optimizing is it's theta, the parameters of the neural network that determine the nonlinear function. And basically, we do exactly the same thing. We compare it with the observations, and then we also compare it to the solution of the solver. So basically, what we are learning here is a nonlinear function and not a single scalar value. So basically, this nonlinear function captures global patterns that determine a little bit like the spatiotemporal variability of this parameter. So if you think about this is basically like a parameterization, an empirical law. It captures like patterns in the data, and it provides much more information than just like a classic inversion. And a very important detail here, of course, like here we are not just doing backpropagation of a neural network. We are basically backpropagating through a PDE solver, which is quite complicated. So this, of course, it means that we need to be able to differentiate the whole thing. And this is exactly why we're using the Julia programming language, because the Julia source code is differentiable, so we can basically get the gradients for free. And the whole ecosystem of scientific machine learning of Julia has been built around this coupling of the differential equation solvers and all the machine learning machinery. So yeah, this has been perhaps one of the trickiest parts to implement for this project. And maybe now that, like, we have a little bit more the concepts of how this work. This is kind of like a figure that summarizes a bit like how this works. So this is, of course, our initial state that we want to use for our simulations. And here we have the PDE solver that we run forward from T0 to T1. This is the mass balance that for now we keep outside of this UDE part. I mean, we fit it, but it's not like simulated by a neural network. And what we do is like we parameterize a subpart of the ice flow dynamics with a neural network, and this is what we do here. And basically, like the neural network provides the solution of this subpart of the differential equation, which we run forward. And then we compare it to two observations, basically. In this case, like the PDE computes the evolution of the ice thickness, but then what we do, we perform just an inversion in order to get the surface velocities of the ice for that period of simulation, because those are the main observations that we have from satellites that we use to constrain this. So surface velocities of the movement of glaciers are a really good proxy of the rheology and their ice flow. So this is what we're using to basically in the cost function. So of course here we basically we compute the error. Then this allows us to optimize the parameters of the neural network. Basically, we need to go backwards in the solution of the PDE, and then we update the parameters, and then we run forward again, we compute the error, and basically this is sort of some, like, it's the classic like kind of backpropagation training, and we train this until it converges or not. So yeah, what we did basically in order to prove that this work, of course, it's before jumping and using it in the wild with like real observations, it's best to understand if your system works in a controlled environment. So what we did is we created this toy model basically, and we gathered 17 glaciers around the world with different climates. And what we did is we basically generated like some sort of like fake law that we wanted to capture with noise. And we created like a kind of like a perfect crime scenario where we generate like this reference data set that we know, and then we try to like go backwards and learn the original function from it. So basically in blue, you can see this like the kind of the fake law that we created that maps the viscosity of the ice to, for example, the local climate. And then we ran forward like simulations for 5 or 10 years for these glaciers, and then we added noise to the law, and we basically use that as like observations. And with those like velocities for that period, then we asked the model to invert and see if the neural network could learn the mapping. And here in orange, we can see that this is exactly what the network learned. This is not the final law that we use, but anyway, it's just the only GIF that I have like available now. So this is a bit like how we saw that this was first robust to noise, and actually how it can learn indirectly from observations. Because basically the neural network or the method is not seeing the values of A, it's just seeing like basically the impact of the perturbation of a change on A on the whole trajectory of the PDE. And yeah, like to start a bit like wrapping up, of course, this so far has been like very methods based, but the idea is like now we're finishing a paper on this and we want to, of course, apply it. So the idea of these methods is to apply them on global functional inversions of ice rheology. So basically like the physical properties of ice and how they move and how they also slide on their beds. And so for this, we want to use like all the global data sets that are available in the community, basically. So like field data from ice thicknesses. Well, we also have like global coverage for ice surface velocities from a recent paper, and also some more detailed data sets for some regions. And then we also are going to use all the digital elevation models that are available at a global scale. And then the idea, of course, is to make these functional inversions of ice rheology. So try to discover parameterizations that could be useful for global glacier models. And basically, yeah, try to better constrain the diffusivity of the ice. So both the creep, so the internal deformation of the ice, but also the basal sliding, because glaciers actually move through these two processes, which actually makes it even more complicated because there's some equifinality involved here. So yeah, basically wrapping up a little bit, like so far, the main challenges that we have encountered has been mainly related to the use of automatic differentiation and the tools under development in the Julia ecosystem. So at the beginning, right now it's much more stable, but at the beginning, basically we were working with tools that were constantly updated. Basically, we were working on applications on tools that were still under development. So we were so close to the releases of the developers that basically this involves sometimes like getting burnt a little bit because some tools, for example, the API changed completely or the library name changed. So we had to completely destroy all our tests. So we had to basically change like big parts of the model. These are a bit like the price that you pay when you try to use like very, very new tools. But right now it seems that it's like slowly converging, it's getting better. And yeah, I would start encouraging people maybe to try this. But before, like 2 years ago, it was pretty rough. And then it's also something quite cool, like this intersection between differential equations and machine learning is very new. So we're seeing behaviors, so we're seeing like interactions or like characteristics that we still don't quite understand. For example, we're seeing some sort of like implicit regularization from this. We haven't used any regularization in the neural network, and it never overfits. So this is actually quite interesting, and we want to try to understand a bit better like all these more like fundamental questions of the modeling. And then, of course, yeah, there's a bit more on the near future. We want to apply this to large scale, like remote sensing data set from satellites in order to improve a bit the physics that we include in global models. So yeah, I think this is all from me. So thanks a lot for your attention, and I'm happy to take questions.
Okay, thank you. Thank you, Jordi, for your interesting presentation. So is there any question from the audience? Again, feel free to type in the chat or turn on your microphone and ask a question directly to the speaker.
Yeah, if you don't mind, I've got one question.
Sure.
So, well, thanks very much for the talk first. And I think that it's a really nice problem. And the way that I see it is that, so if a motion of a glacier is dictated by something which we can't directly measure, such as the what is happening at the base or the subglacial hydrology and so on. So we can't directly measure this, but we've got some observations which we can spatially and temporally connect to those processes. But are you somehow accounting for those spatial and temporal correlations? Do you think that this would be good to do, maybe? Or
what do you mean by like spatial and temporal correlations? In which sense?
Yeah, so I guess that some of the observational data can be the velocity of the surface or the changes in the mass balance and that so on. So I guess where you're actually observing this data, and I guess that you are only taking out of all of that just one number for your ice viscosity. So it seems to me like it's a kind of an like a mean of all those processes.
Yeah, but I mean, it depends on what you I mean, this is all like about model design. So basically, you wanna that's if you wanna really isolate the dynamics, we know that, for example, the surface velocities of glaciers are mostly impacted by the dynamical aspects, and they are not perturbed so much by the mass balance component. So like if you use, for example, altimetry, so like the surface elevation of the glaciers, then that information carries a lot of like physics or information from both physical processes, whereas with like the surface velocities, we can isolate that better. in this case, I show like the inversion of the A parameter just because an example, but like in real life, we wouldn't necessarily have to do that. Like we can design whatever we want. Like a problem that we have, for example, is like this diffusivity of the glacier. So the way it moves, as I said, it's due to internal deformation, but at the same time sliding at the bed. So since observations come from space, so from the surface, they integrate these two processes. So this makes it quite hard. If we only have one snapshot, there's no way to disentangling them. So what we need to do is precisely look at high resolution, temporal resolution like data when there's fluctuations between winter and summer, and then go at these peaks, for example, the peak in winter and the peak in summer, and use hypothesis saying, here it's mostly in this regime where it's dictated by internal deformation, and this is more like in this regime where it's like dictated by sliding at the bed. So then you can like, you know, disentangle the two processes and invert. Otherwise, there would be like an infinite amount of like possibilities. So like I would say that like the model design is completely like dictated by the observations available, and then it's up to the to your like knowledge of the physics of the application that you do to design the model correctly. It's not like a classic data-driven machine learning where you, of course, you need to know a bit better, but like you can just feed a ton of data and it will automatically like use what it needs or not. There, like you really need to design your model in a very like careful way, understand very well like the physics that are involved.
That makes sense. Thanks very much.
Are there more questions from the audience? So if I may ask a question then. So I saw that there was the law, the viscosity coefficient versus temperature.
Mm-hmm.
So I wonder whether there are, I mean, maybe for the viscosity, but also for other quantities, is there a way then to embed more physical knowledge into the system? Because I don't know, maybe there are already available some empirical laws for how the viscosity changes with temperature, or maybe this is true for other quantities. I remember that like there are other parameters that needs to be determined in this equation. Like if I remember correctly, the variable n, for instance, is another one that needs to be calculated.
Yeah.
And so, well, and also another question connected to that is, how do you extend this approach to take into account optimization across multiple parameters? Like maybe do you end up in like saddle point problems or no?
This is exactly what I meant before. Like you could have a ton of like that degeneracy or like of like finality, where if you're, for example, here both A and N do the same thing, and also it's like it's the power law of the deformation. So this will totally change like the shape of your power law, and we know that in the wild it's mostly around 3, but like it ranges between 2 something and 4.
Mm-hmm.
So yeah, you could either fix it and then compensate with the other one, but like that's why we think that like maybe what's best is just like, since here we have like mostly 2 degrees of freedom, we have N, we have A, yeah, because this H is the ice thickness that we know, this is the surface gradient that we know, and then and this is actually like the simple version, because in theory we have 3 degrees of freedom. C is the velocity at the bed, A is the viscosity, and N is the power law. So if you have 3 here, maybe like you could either put like 3 neural networks and put like proxies in each neural network that disentangles them, so like that they are not converging, like that you can basically like separate the regimes. Or another approach that would also be valid, that would be kind of like the most targeted approach, but you could also say, okay, so all the diffusivity is a neural network, and it just feed, of course, H and S, the data I have, and then these are just constants. This is the density of ice, is like the gravitational constant, and then you just feed like to this like larger neural network all the proxy data that could explain this. So whatever like it's normally used in the parameterizations or on the current equations, and then you ask it to basically learn some sort of like new ice flow law from scratch. So instead of kind of like taking the mechanistic model that exists and trying to fit the parameters to that model, you could like reverse the question, say, okay, I have some observations. What is the model from scratch that describes best these observations, you know? So it's another way, but you can redesign it in any way you want. You can make the networks very small, or you can make them very big.
And have you also considered like gathering data from different sources? Like I don't know if you have plans of like instead of only using like pictures from satellites, if any other information is available that in the future that you're considering.
Yeah, but the problem is like field data for glaciers is like extremely costly, and there's I mean we are using mostly for the mass changes, like normally like glaciers are, I mean we have observations from space, but mostly they are done since the 20s or the 50s, mainly by alpine nations, so like Switzerland, France, and Austria. And we have lots of observations there, but it's only for like few glaciers, and those are like kind of like high quality, high temporal resolution and spatial resolution. So of course we're using everything, and it's also a matter of like the way you see this. Like right now, these methods, maybe we can only take them so far, but this having this method like in place, it's some sort of like almost it does data simulation basically. You do like you kind of like do in inversions, and you can put anything you want in the loss. And the idea is like maybe now we can only like, you know, invert something with like a limited amount of quality, or like with a lot of noise, or too much like okay finality. But maybe like next year there's a new like data set like that it's much better, and that will like pinpoint much better some dynamics in some part. And then so the idea is like to just fit in like new data as it comes, and dynamic like in a iterative way to improve the kind of like the laws that we're learning.
Yeah, I mean, we also hosted a similar talk. I mean, similar in terms of topic. There was a company called RSS Hydro, and their goal was to basically forecast the impact of flooding using images coming from satellites. And they were able to have a procedure that would allow you, from machine learning, also to take into account the presence of clouds. So, I mean, this is just for maybe some later brief, sorry, but in case you're interested, I'm happy to share with you the slides or the coordinates so that you can have a look. I don't know, maybe they're willing to share part of it.
I would love to.
I thought the two things were related, yeah.
Cool. Yeah.
Okay, so more questions from the audience? Okay. Well, if not, I would like to thank our speaker again. And well, Jordi, it's been a real pleasure. The talk was really interesting. And so just in case you or other people of the audience know anyone that would like to give a seminar, please let us know. We still have a few slots available before the end of the year. Otherwise, well, let's thank our speaker again, and we'll see you in a couple of weeks' time.
Thank you very much.
Thanks again.
Bye-bye. Have a nice day.